So in the previous modules of the Schrodinger wave equation for simple harmonic oscillator, we talked about how to derive eigenvalues and eigenfunction for simple harmonic oscillator, both using a ladder operator as well as power series method. So we do have with us the different eigenfunctions and different eigenvalues for simple harmonic oscillator. Now in this particular module, we are going to use those relationships, means eigenfunctions and eigenvalues, to establish some of the principles of the quantum mechanics, as well as we will I will tell you that the purpose of finding out the eigenfunctions of simple harmonic oscillator, what physical quantity we can get from these eigenfunctions value. So we will derive some of the physical properties, we will obtain some of the physical variables from this eigenfunctions. But before that, I am going to talk about that how uncertainty relationship can be obtained from the wave functions of simple harmonic oscillator. So for the ground state wave functions, what we derived for simple harmonic oscillator is that psi naught is equal to this one beta. Psi naught is equal to beta divided by pi raised to the power 1 by 4 exponential minus beta x squared divided by 2, where I said you that this is your normalization constant n value, and this is your Gaussian function. This particular function does not have any Hermite polynomial because it's for the ground state. So in the ground state, if you want to find out the expectation value of a particular quantity, then if you remember the postulates of quantum mechanics, what we said, that expectation value of a particular quantity, say x, can be obtained when you differentiate this with respect to psi x operator, psi star x operator d tau divided by psi star so d tau. This is the postulates of quantum mechanics, that if you want to find out the expectation value, or this we write as average value also, average value like this one, then this relationship is used from the postulates of quantum mechanics. Now here in the denominator we have psi star psi d tau, and this condition psi star psi d tau for a normalized wave function, you know, if it is a normalized wave function and you integrate it from minus infinity to plus infinity, what you get is equal to 1. So if you are using a normalized wave function, your denominator becomes equal to 1. Only numerator you have to solve. Okay. So since we have a wave function here for a simple harmonic oscillator, the normalization constant is there and it is a normalized wave function. So only numerator of this we have to solve. And if you solve the numerator, what is numerator? Integral from minus infinity to plus infinity. Then you have the first wave function beta divided by pi 1 by 4 raised to the power 1 by 4 exponential minus beta x squared divided by 2, and this is your operator for the position, which is multiplying by x. And then again the next wave function beta divided by pi raised to the 1 by 4 exponential minus beta x squared, where you do not have any I term, so it's not psi complex conjugate. Okay, so this integral we have to solve, and in this integral, if you want to solve, then this beta divided by pi raised to the power 1 by 4 and this beta divided by pi raised to the 1 by 4 is a constant, so bring it outside. This becomes beta divided by pi raised to the 1 by 2, and then within the integral you have x multiplied by exponential minus beta x squared. So one of the function is odd, another is even, so this integral will become equal to 0. So the average value of x, what you will get is 0. Okay. For finding out the simple harmonic oscillator, we have seen in the case of particle in a one-dimensional box that you need x value, average value of x square, average value of px, and average value of px square. So the one of the quantity x we have determined is equal to 0. Okay, is equal to 0. Then the next quantity is x square. So again the similar way one can obtain the x square value. The numerator we have to solve from this expectation value relationship, and that is minus infinity to plus infinity beta divided by pi raised to 1 by 4 exponential minus beta x squared divided by 2. This is one psi, then this is your operator, and this is another psi. Okay, so psi and operator. This is what is your quantum mechanical postulate tells you about finding out the expectation value. This we have done earlier also, so it should not be an issue. Okay, if you solve this integral, what you get is this one. Now this we can write as simple multiple of x square. Instead of this one, we can remove this one and we can write x square exponential minus beta x square, because it's a position operator is simply multiplying by the position, okay, x value. Now here it is not, both are even quantity, x square exponential minus beta x square. So this integral will not be equal to 0, and since it is an even function, so we can use this relationship that from minus infinity to plus infinity integral you can write as 2 from 0 to infinity. So if you use this relationship, then what you write for x square beta divided by pi raised to the power 1 by 2, then for this integral we will write 2. Then now the integral limit is changed from 0 to pi. It was initially from minus infinity to plus infinity, and when you change the limit you write 2 here. Okay, then you have x square, remove this cap, and then x square exponential minus beta x square divided. And this is a standard integral. This integral is a standard integral, and the standard integral value is this one. I will write a standard integral. In most of the cases, integration we will not do a stepwise, we will use standard integral. So this standard integral if you use, then the equation which you get is 1 by 4 pi raised to the power beta cube. 1 by 4 root under pi root under beta cube. Okay, so this is your integral value. This is the value of integral. Okay, and this gives you finally 1 over 2 beta. So the expectation value of x square we reach at 1 over 2 beta, and expectation value of x is 0, that we have done. Okay, now the next quantity which you have to find out is the expectation value of px, linear momentum. Okay, so what is the px value? And the only thing which you have to change is the relationship remains same. Numerator you have to use, denominator becomes equal to 0 because the wave function is normalized same way, and the only thing changes is operator. Now the operator is this one. This is the operator for linear momentum. Okay, initially for a position we use x, for momentum you use h cross by I ddx. Okay, so if you use this operator, here you have to differentiate. You bring this outside, beta divided by pi raised to the power 1 by 2, h cross I you can take outside, then this exponential term and ddx of exponential minus beta x square divided by 2. So if you differentiate this, what you get? The differential is minus beta x exponential minus beta x, because if you differentiate it, what it will be? It will be 2x divided by 2 beta 2x divided by 2, so it will be beta x. Okay, so minus beta x will be this is your differential after differentiation. Okay, now if you rearrange this one and bring minus beta outside the integral, then what you have? You have again x into exponential minus beta x square. Again you see an odd function and an even function. So this integral will become equal to 0. And if this integral becomes equal to 0, then the average value of position linear momentum px also becomes equal to 0. So I will write px average value is also equal to 0. Average value of x is 0, average value of px is 0, average value of x square is 1 over 2 beta. Okay, the last quantity which you have to do is px square. So for px square, the only thing will be the square of this particular operator, rest of the thing will same. And for px square, we can write like this one, a square of the operator px square. Okay, and rest of the thing is same. The two wave functions, beta divided by pi raised to the power 1 by 4 exponential minus beta x square divided by 2, and then again this is also the same wave functions, and you integrate it from minus infinity to plus infinity. So rearranging this equation will give you minus h cross square will come outside, and now it is a double differential of exponential minus beta x square divided by 2. So if you double differentiate it, first differential we have already done, it comes out to be this one. Okay, first differential. Then second differential if you do, you get this one. Minus beta you bring outside and then you differentiate this one, x exponential minus beta x squared. Now it is two terms, one is x, another is exponential term. So differentiate one keeping the second constant, and then differentiate first keeping the differentiate second, then keeping the first constant. The normal procedure of differentiating two functions. Okay, so here we have differentiated x, which comes out to be 1, and here we are differentiating with respect to this exponential term. X remains constant, x we are not differentiating, we are differentiating. So the first in the first half x is differentiated, in the second half exponential term is differentiated. Okay, so you get this differential. Same differential we are repeating. It's not, it appears to be a huge equation, a big equation, but it is the same equation which we are writing time and again. So once you learn for one at one place, then it becomes very easier for other places. It's the same differentiation of exponential minus beta x squared divided by 2, which we are doing time and again. Okay, sometime alone, sometime with another function x or x square. Okay, so this we get, and the value of, so we can further, the same equation is here, and then we can take this as a common, exponential minus beta x square, and then it becomes 1 minus beta x square divided by into dx. Okay, so now we have two integrals. One is for exponential minus beta x square dx, and another is beta will be common and x square into exponential minus beta x square dx. So we have two different integrals. One is this one and another is this one. Okay, and again see, this integral you have already done in the previous example. Okay, and this integral also we have done somewhere, and so this comes out to be beta divided by pi raised to this all this integration terms before the integration remain same, and then this integral is root pi divided by beta, then beta, and this will be 1 by 2 root under pi divided by b raised to the power whole cube. Okay, so once you have this, we have done these terms, this comes out to be beta divided by pi into beta h cross square pi divided by root beta, and then 1 by 2 pi divided by beta, because you have 3 by 2, so one of the beta will go. Okay, and you will have beta raised to the 1 by 2 only. Okay, so what you get is beta divided by pi raised to the power half beta h cross square 1 by 2 pi divided by root beta. It's root beta minus 1 by 2 root beta, so it will be 1 by 2 root beta, and this comes out to be beta h cross square divided by 2. Okay, so we have px square expectation value as beta h cross square divided by 2. We have x value equal to 0. We have x square value equal to 1 by, I think, root beta. Let me see, let me check it. 2 beta. Okay, so 1 by 2 beta, and we have expectation value of px is equal to 0. With these four, we can go and find out the uncertainty relationship. The uncertainty relationship, we have used this relationship earlier also, so there is no point in talking about this one. Delta x and delta p relationship we have used in particular one-dimensional box. If you put the values of the which we have determined, it comes out to be delta x into delta p is equal to this one, 1 by root 2 beta, and then h cross root under beta divided by 2, so it comes out to be h cross divided by 2 or h divided by 4 pi. So using the eigenfunction of simple harmonic oscillator, one can again obtain the uncertainty relationship, which is one of the fundamental relationship of quantum mechanics. Okay, and so twice we did it, one in case of particular one-dimensional box, and again we did it in the case of simple harmonic oscillator. Okay, what other use we can do with these wave functions? Can we find out the other physical variables with these eigenfunctions? Yes, we can find out. Okay. So now try to find out the kinetic energy of simple harmonic oscillator. And the kinetic energy relationship, you know, from the Hamiltonian, again it is the same thing, same expectation value relationship we are using, the operators we are changing. Okay. And if you remember, the Schrodinger wave equation was minus h cross square divided by 2m minus h cross square divided by 2m del s square plus v, okay, psi is equal to E psi, where this is your potential energy V and this is your kinetic energy. This we can write as minus h square divided by 8 pi a square m. So the kinetic energy operator is minus h cross h square divided by 8 pi a square m d square by dx square. So this is your, in the red I have written, kinetic energy operator. Whatever operator you use, you get the expectation value of the same physical quantity, and the t term I have used for the kinetic energy. So if you use this operator, then see the derivations, because minus h square divided by 8 pi square m I have brought outside. Then you have this first exponential term, second exponential term, and in between you have double differential d square by dx square. And again you see the same differentiation, nothing new. Okay, same differentiation we are doing time and again. So you have to learn only once and then apply at many points. So the kinetic energy becomes equal to minus h square divided by square. This is your differentiation. This you obtain after differentiation twice, because we have done it earlier. So in the one step itself I have written. Okay. And again, if you have to integrate, then you will have to integrate this and you will have to integrate this. And see these two integrals, this one and this one, both you have done earlier. Okay. So with this integration, what you get is root under pi divided by beta and 1 by 2 root under pi divided by beta cube. Using these relationships and then doing the simple derivations, what you find is kinetic energy is beta h square divided by 16 pi square m. Okay. So the average value of kinetic energy we can obtain using the operators for kinetic energy. Okay. Same way you can go ahead and you can do any other calculations. You can use potential energy operators, and let's see if you use the potential energy. What is the operator of potential energy? Kinetic energy is fine. The potential energy is V in the Hamiltonian, and V is the potential energy which arises because of a force acting on the system. If there is no force, V will be 0, because in particular in a one-dimensional box you have seen that we put V is equal to 0. Okay, but in case of any system where there is a force, there will be a potential energy, and potential energy of harmonic oscillator we have calculated in the very first lecture of simple harmonic oscillator, that a classical harmonic oscillator has a potential energy is equal to 1 by 2 k x square. So the operator also will be the same, 1 by 2 k x square. So if you use that and you try to find out the expectation value of potential energy, then you have to use the operator 1 by 2 k x square. Okay. With this potential energy value 1 by 2 k x square, if you use, again you see it is the same integral which you did time and again, x square exponential minus beta x square divided by dx, and the value is, integral is this one. Okay. So k divided by, and this gives you k divided by 4 beta, and beta is what? Beta is 2 pi divided by h root under mk. This in the very first slide of the simple harmonic oscillator, you go and find out beta we have taken like this one. And if you do potential energy calculation, then you find that you get h divided by 4 nu naught. What did you find for kinetic energy? Oh, this was the this was the kinetic energy, and from this kinetic energy what we can obtain is if you use this beta value, then finally what you get kinetic energy is this one, h divided by 4. So kinetic energy T is actually h divided by 4 into nu naught. And if you go for potential energy, then also you get the same value, h divided by 4 nu naught. Okay. So see how we can use the eigenfunction in order to get the physical quantity, position, momentum, kinetic energy, potential energy. All this we determine from the simple relationship of eigenfunctions of simple harmonic oscillator, which we derived. Okay. So that's the beauty of doing these calculations. That's why I said you that the whole idea in quantum mechanics is to find out the eigenfunction. Once you have the eigenfunction, then there are rules which you can apply and you can find out the physical variables. Okay. If we go for finding out the maxima of the ground state wave functions of simple harmonic oscillator, I have shown you the graph, and if you remember the ground state wave functions, if this is your potential, then ground state wave functions was like this one. Okay. So it goes beyond the classical limit I said you in the previous module. Okay. And the maxima which I said you comes out to be here. In this direction you have plus x direction, here you have minus x direction. So it goes minus infinity and plus infinity. It goes to plus infinity, it goes to minus infinity. So the integral from plus infinity to minus infinity. And the graph tells you that the maxima is actually at x is equal to 0. So can we find out from the eigenfunction this particular observation of the graphical observation? You can find it out. For finding out the maxima, what you do? You differentiate the function with respect to the variable and equate it to 0. And then whatever value you get for the function could be either maxima or minima, and then you do for double differentiate, that you are aware of doing it. Okay. So if we put the value of, if you differentiate psi naught ground state wave functions with respect to x, what do you get? ddx of the ground state wave function is beta divided by pi, same 1 by 4 exponential minus beta x square divided by 2. So the differentiation is this one. This differentiation again you have already done. So let us see what do you get. You see the differentiation is this one. Okay. The differentiation, if you differentiate it, you get this one. And we say that the above equation is satisfied when the value is x is equal to 0 or x is equal to plus minus infinity. It means that when if you put x is equal to 0, this LHS will be 0, and if you put x is equal to plus infinity or minus infinity, then exponential term will become 0. Okay. So this equation is satisfied only when either x is equal to 0 or x plus minus infinity is equal to 0. Okay. Now, in order to find out the maxima, you will have to differentiate it again, second differential. So the second differential of the function, that's the same function, will give you this particular, this remains same, and then you have minus beta, this minus beta comes here, and then for second differential with respect of x into this function. This already first differential is done. So beta we have taken out, minus beta I have taken outside, and then the second differential you do for this function, and then the second differential gives you this particular equation. Okay. So you can bring two out, you can see that if you rearrange this one, you have exponential, you can take this outside, this outside. So whatever you have is, and multiply this minus beta, so you have is this one, minus beta plus beta square x square. Okay. So this particular double differential of d square psi naught will negative at x is equal to 0. You have minus beta and you have plus beta square x square. So at x is equal to 0, this will become 0, and you have a negative value of the differential. So the maxima is at x is equal to 0. So what you observe, that in the ground state of simple harmonic oscillator, the function beta divided by pi raised to the power 1 by 4 exponential minus beta x square by 2 has maxima at x is equal to 0. And the same thing we have shown in the graph also. In the graph also you see that at x is equal to 0 you get a peak for the first eigenfunction plot. Okay. Now can we do it for the second excited state also? We can do it for the excited state also. Determine the value of x for the maxima of first excited state wave functions. You see the difference between the ground state wave function and the first excited wave function is that you have another quantity also which is called Harmonic polynomial, and this part is Harmonic polynomial part. Okay, this is normalization constant which you have. Okay, and now you have this part as the psi 1 function. Okay, so besides Gaussian function you have other things also, and this makes you the x is the value of Harmonic polynomial. I think 2 root beta is also in the normalization constant anyway. So whatever be the if you have to find out the maxima of this function, again what you have to do, you have to differentiate psi 1 with respect to x, and if you differentiate psi 1 with respect to x, the same differentiation which now if you combine these things, this is the only variable, and so ddx becomes x ddx of x exponential minus beta x squared divided by 2 you have to find out. Again you have done it, keeping x, differentiating x and keeping the exponential term constant gives you this one, then keeping x constant and differentiating exponential term gives you minus beta x exponential minus beta x squared divided by 2, and you finally what you get is this one. Okay, so what does it mean? It means you have 1 minus beta x square is equal to 0, or 1 will be equal to, if this equation has to be valid, then 1 minus beta x square divided will be equal to 0. So x will be equal to plus minus root beta. Okay, and then beta is equal to, since beta is equal to this one, if you put this value, x comes out to be this one. But it is the first differential only. So in order to find out the maxima, you need to do the second differentiation also. But instead of doing second differentiation also, what we can do is in this particular case, we can equate the classical energy and the quantum mechanical energy. So classical energy is 1 by 2 kx square, and the quantum mechanical energy which we have found is V plus half h nu, and for the first excited state V is equal to 1, so it will be 3 by 2 h, and nu is equal to what? 1 by 2 pi root under k divided by m. Okay, so this relationship we can use, and we can get the maxima. And if you use, I have knowingly not done it for you, I have left it for you, and you have to show that from these two relationships you may obtain that x as the 0.577 of the maximum displacement in the first excited state. Okay, so this you have to prove. If you equate this, you will get x is equal to this one, x maxima is equal to this one. So x maxima you will put, and then you will find out the value of x, you will get it. Okay, so this is the fill in the blanks which you have to fill, and you have to find out, confirm that whether whatever is written here is right or wrong. Okay, having done this and using these equations, we have finished almost everything about the simple harmonic oscillator. We have started with classical harmonic oscillator. We talked about its solution, its energy. We talked about its solutions. We talked about everything. But what is the use of doing this? The actual in chemistry where we use it, that if you have two atoms A and B which is bonded together, and atoms vibrate and show a harmonic oscillation, then we can apply these principles of quantum mechanical simple harmonic oscillator to these vibrations. And the relationship which we have obtained, EV is equal to V plus half h nu forms the basis of IR spectroscopy. And you know the application of IR spectroscopy, if you do for organic chemistry, you find that all organic molecules, when you synthesize or any other molecule, IR is the normal routine experimental techniques which is used in the chemical laboratories. Okay, so but the theory behind this is application of Schrodinger wave equation to simple harmonic oscillator. Of course, as long as the oscillation is harmonic, then only this equation is applied. Otherwise, you know, anharmonic oscillations are also crop in, and then the relationship changes. Okay, so anharmonic terms also is introduced. But the whole idea of doing this simple harmonic oscillator is to get the theoretical basis of IR spectroscopy. Okay, which is one of the most important physical techniques for characterizing molecule. Okay, now we talked about the simple systems, and again gradually we are going to the higher systems. So we will go to, in the next module I will talk about the rigid rotors. Till now whatever we have done is the application of Schrodinger wave equation in Cartesian coordinate. The moment you go for a angular motion and rotational motion, then we apply the Schrodinger wave equation in terms of spherical polar coordinates, and this will be the topic of next module: how to apply Schrodinger wave equation to a rigid rotor. What is the rigid rotor? How do we get the energy for the rigid rotor? And the wave function for the rigid rotor. Okay, so we will start this rigid rotor in the next module. Thank you.